Yeah, Siddharth. Thank you. Hello. Thank you.
Okay.
Do we have to say this? My name is Sejal.
Okay.
Oh, my name is Sejal.
And my name is Siddhant, and the title of my talk is Demystifying Garbage Collection in Python. And I hereby agree to abide by Pycon APAC Code of Conduct and consent to being recorded and streamed.
All right, good afternoon, everyone, and welcome again to Pycon APAC 2024 for the second session or our last session for today, hosted here at Nadlatul Ulama University of Jakarta. My name is Nadla, and I will be your moderator for this session. So our speaker for this session today will be Sejal Gupta and Siddhan Gupta that will be presenting on the topic of organized chaos demystifying garbage collection. And without further ado, please welcome our amazing speakers.
Thank you. Thanks, Nabila. Hi, everyone. Once again, welcome to PyCon APAC 2024. I'm Sejal.
And I'm Siddhant, and we'll be speaking about demystifying garbage collection in Python.
So we know you've developed awesome websites, built AI-powered solutions. And yesterday itself, we witnessed some amazing real-life complex applications in the workshop. But have you wondered about a niche topic in Python, like how Python manages memory for you? Or how Python prevents memory corruption? And who really owns the memory?
It's all done automatically. No, really. You just need to create an object, and Python virtual machine handles everything, the memory needed, and where it should be placed in the memory layout. It unburdens us from all these questions. Should I free the resources, or whether or not should I need to intervene manually? So hi everyone and namaste, greetings from India. I am Siddhant, a software engineer at Salesforce, and it's been around 3.5 years in this industry. And I love turning ideas into code. And apart from work, I enjoy playing flute and tennis and basketball. Looking forward to connect with you all.
And hi everyone, I'm Sejal. I'm also a software engineer from India. It's been 3.5 years for me in the industry. A little about me. I love building data-driven systems and applications around it. Apart from that, I also love knitting, reading, bicycling, and solving Sudoku. So I'll definitely try Agriya Sudoku game. And I've also mentored 300 plus women in tech through a community that I founded in college with plus women in tech. So let's get started. Today we'll be talking about memory management in Python and some complex aspects around it. We'd also touch upon variables and what goes on in the background. We'd also discuss in detail about some advanced topics in garbage collection like reference counting, GIL, and generational GC. We'll also see if you really are missing out on a step, which as a matter of fact, you should be doing to make your applications faster and more optimal.
So let's warm up a little and begin with an example. So these are individual test cases on the screen. So can you guess what would be the outcome of this? Would any test case be false? Any guesses?
Any trues, any false?
So just a small information, the double equal to operator checks if the two variables have the same value, and is operator checks if two variables point to the same memory location. So if you are thinking all of them are true, well, no, one of them is false.
but only one of them.
So let's have a look at what's going on in the background and why we see what we see. So in order to understand how memory management works in Python, we first need to ask ourselves what is a variable. Of course, everyone knows variables are labels, but what we really want to divert your attention towards is that variables in Python are just references to objects. They don't hold the value directly, instead just point to object stored in the memory, and that is unconventional. Like in other OOPS languages like C, C++, if I create two variables with same values, they will both point to different memory locations and act as individual objects. And if we reassign the value to some variable, its memory location won't change, just the value will be updated at that memory location. However, if we do similar in Python, we will notice both the variables will be pointing to the same memory location. And if we reassign a value, we will lose a reference to the memory location which has 49, and now it will point to a different memory location. So let us say if I have 100 variables with value 49, we will have 100 memory locations in C and C++, but just one object will be created in Python, and all the 100 variables will be pointing to that single object.
And this is what we call as object internal, where Python reuses the objects and does not create multiple different objects if it holds the same value. And this helps Python reduce memory footprint and improve performance. Having said that, Python automatically interns small integers and short strings, but not container objects or mutable objects like lists and dictionaries. So revisiting the same example from before, in the first two test cases here, 10 and Pycon APAC are both either short strings or small integers, and hence both of them will point to the same memory location. However, in the third case, where A and B are two different container objects, here they will not be interned in Python, and both the variables will point to two different memory locations. So the key point here is that objects in Python are managed through references, and Python deals differently with mutable and immutable types.
So let's have a quick glance now at how Python allocates resources to its objects. Well, everything in Python is an object. All the entities, including the numbers, strings, functions, classes, and even modules. So internally, every Python object holds four things: its type, its value, identity, and a reference count. So what is a reference count? Every object in Python has an associated reference count which tracks how many references point to that object. Let's see how does the reference count of an object changes. So in this example, we are setting the variable x to be namaste. So when we set the variable x to be namaste, it increases the number of references to namaste object by 1. Later on, we say y is equals to namaste. As we have seen in object interning, instead of creating a new memory slot for namaste, it just adds another reference to it. So now our reference count becomes 2. Or when we use it in a function, that will also create a temporary reference, making our reference count 3. And if we put it in a container like a dictionary or a list, that will also increase the reference count. So now the namaste object has a reference count of 4. Whenever a reference to the object is deleted or goes out of scope, Python decrements the reference count. So in this case, this will decrease if I remove it from the container or delete the container itself, or when the function ends, or when I reassign a variable y to some other value, or if we delete a variable x. So now you see our namaste object has a reference count of 0. And when that happens, boom, garbage collection comes into action. Python now knows to remove this from memory.
I know reference counting seems pretty simple to implement. When reference count is 0, objects are immediately deleted from the memory. But it also comes with a little bit of space overhead, because Python will now need to also hold, other than the object, the reference count of the object. And then every time a reference to an object is changed, the reference count will need to be either incremented or decremented, which adds on some performance overhead. Now, Python allows multi-threading, which definitely makes our lives quicker.
Woohoo.
But that upsets garbage collector. What do you think would happen if two threads try to modify the same object parallelly? Yeah, this could lead to race conditions like dirty read-write problems and can lead to memory corruption. For instance, if you remember our good old object namaste, let's say two variables are pointing to it, A and B. Since there are two variables, the reference count of namaste would be 2. Now let's take the first scenario. When thread 1 tries to delete A variable, so algorithmically it will first read the reference count, then it will decrement the value of the reference count. And once it does that, variable A gets deleted from the memory. Then thread 2 starts working. It does the very same thing. It will read the reference count, decrement it by 1, making it 0. And both A and B will be removed from the memory. The object namaste now has a reference count of 0. That means Python can very easily come and collect it. But we know multi-threading is not idempotent. So let's see another scenario. Now, thread 1 will again read the reference count as 2, starting from the beginning, sorry. And here, thread 2 now comes into action and also reads the value of the reference count. Before, it gave the chance to thread 1 to decrement x. Now, thread 1 and thread 2 both will decrement it to 1. And we can see that namaste object is still in the memory, even though A and B have stopped referencing to namaste. That means garbage collector cannot come and collect the namaste object. And this is a clear example of memory leak.
And there comes GIL to save the Python world. Let's see what is GIL. So GIL is a global interpreter lock that allows only one thread to execute Python bytecode at a time, thereby preventing race conditions and saving us from the pain of managing manual locks on our own. Multi-threading with GIL works well with input-output bound tasks like network operation, file read-writes, as these tasks often spend time waiting on external resources during which GIL can be released, allowing other threads to run. But come on, even Superman can fall from a chair. Similarly, GIL adversely affects CPU-bound tasks. Since at any instant only one thread can hold the GIL and execute Python code, this leads to inefficient use of multiple CPU cores. But don't worry, there are some alternatives to GIL in such cases. One can use the multiprocessing modules, which create separate processes, each with its own Python interpreter and memory space, thus bypassing the GIL. Or we can use libraries like NumPy and Cython. These tools can help us avoid the GIL and achieve faster execution by compiling parts of a code to the native code itself. And as per PEP 703, Python Enhancement Proposal 703, a disable GIL flag in CPython is also proposed, making the global interpreter lock optional in CPython. And mechanisms like fine-grained locking or atomic operations are used to safely manage memory and data integrity here. This is definitely a very exciting improvement as it has the potential to enable Python applications to take advantage of multi-core CPUs with less effort and overhead than the current methods.
Okay, we accept we lied. There is not just one, but two major problems. First, of unsafe multi-threading, which we saw can be solved by GIL. And second, of circular references. Now, when a group of objects reference each other in closed loop, reference count does not become 0. And this can again lead to corruption in memory. So what is circular reference? Let's see this by an example. Here, we have a person class, and it has two attributes, name and a reference, OS2. Let's create a person Alice and a person Bob and refer to them by two variables. So the reference count of these two objects will now be 2. And let's say Alice owes to Bob and Bob owes to Alice. In that case, reference count increases. But what happens if we delete these two variables? The references of A and of B to these objects will definitely be removed, but the circular reference will still remain. And because of that, there will be a residual reference count in the memory, which will not allow Python to remove these two objects from memory. So ref count alone cannot solve this problem. Most languages use tracing techniques like mark and sweep algorithm to solve this problem. The mark and sweep algorithm first prepares the root list. It then traverses the list. The list is mainly comprised of global variables, variables on stack, and all the other active objects. It then traverses the root and performs a depth-first search. It marks all the reachable nodes as live, and all the unreachable nodes are then garbage collected.
Well, pretty good. But these tracing techniques are very time complex. And as you may know that during garbage collection, all the active threads are temporarily paused, causing the stop the whole events. And this is necessary also because if objects are modified during the garbage collection, it could lead to inconsistencies and memory errors. And these pauses affect the user experience quite aggressively, especially in the real-time systems or interactive applications like gaming or UI-driven systems. So if we can reduce the time garbage collector is running, that would be pretty awesome. And Python uses generational GC to achieve that to some extent. This is based on the hypothesis that most objects die young, or a tragedy, but not for Python. If you closely observe, usually many objects are created just to store data temporarily, like intermediate results, temporary list, etc. And once their job is done, they are no longer needed. So to achieve this, Python GC classifies container objects into 3 generations based on their age: generation 0, generation 1, and generation 2. Generation 0 holds newly created objects, and this generation is collected most frequently. And if an object survives a collection, it gets promoted to generation 1, and objects that survive further collections are moved to generation 2, which is collected least often. So let's see how does it work. Let's revisit the same example where we had created 2-person objects, Alice and Bob, which are internally referring to each other. Both have a reference count of 2 and are added to generation 0. Now we delete the variables a and b, leading to reference count of both the objects as 1. And this might cause memory leaks, as we discussed before, and would never be cleaned up from the reference counting alone. Now we create another person, Charlie. It also gets added to generation 0. And if we see in this example, the threshold for generation 0 is set to be 3, which is now reached, and Python now knows to trigger a GC collection cycle. So what happens in a generational GC collection cycle? Python makes a list of all the objects to discard. It runs an algorithm to detect reference cycle, which is out of scope of the current presentation, but that is somewhat similar to mark and sweep algorithm that we discussed earlier. And if an object has no outside reference, it's put on the discard list. Here, if you see, Alice and Bob will be put on the discard list, and when the cycle is done, it frees up the Alice and Bob object. And all the surviving objects in generation 0, here Charlie, will be promoted to next generation, that is generation 1. So this is how generational GC works. So just to summarize, we have 2 major phases in generational GC, as we discussed above, object allocation and the collection process. But unlike reference counting, cyclic GC does not work in real time. It runs periodically. In order to decide when to run, each generation has an individual counter and a threshold. And whenever the counter of that generation exceeds the threshold, Python initiates a collection process. By default, the threshold for 3 generations is 710 and 10, which means generation 0 will be collected when 700 new allocations have occurred, and generation 1 is collected when 10 collections of generation 0 is done. Similarly, generation 2 is collected after 10 collections of generation 1 is done. And we can modify when the garbage collector runs by adjusting these thresholds using the GC module set threshold function. And this helps us to tune our GC to the specific needs of our program.
Now, we've seen that Python's GC is mostly automated and works using reference counting. But we've also seen that it's not enough, and it needs a couple more hands like global interpreter lock and generational garbage collection to ensure that even if there is unsafe multi-threading or circular references, it will collect garbage. Now, of course, we can't stop Jim Carrey, but Python lets us intervene in its automated garbage collection process. So let me ask you this question of how often have you triggered garbage collection manually, like gc.collect? Has anyone done that? Well, we know that Python's GC occurs automatically, but sometimes it's good to manually trigger it. Having said that, sometimes it's good to avoid manually triggering gc.collect. Let's say you have a web application or a Django server, which serves a couple thousand requests in a minute. So it will have a few objects or data references like your templates, user data in in the memory. And you should be triggering garbage collection in that case to ensure that memory is constantly cleaned up if there is any residual or unneeded data which is present in the memory. And that can be done based on low server activity or during nighttime. Then, even while training large machine learning models, we've seen, or we generally use NumPy, Pandas, TensorFlow to train our models. And more than often, there are quite complex data structures which come into the memory and sit there, and they are all temporary objects. So again, triggering maybe after each batch of running, of training your models, gc.collect can be triggered. Another example is a web scraper or any long-running background services. Web scraper also collects information from multiple websites and has, again, a couple more HTTP requests while or data which is stored while parsing. So again, triggering garbage collection, sorry, could be helpful in these cases.
Like Sejal mentioned, triggering manual garbage collection can boost the performance, but should we always do it? Well, no. We should be very cautious about it. Let's say we are building a high frequency financial trading system where every millisecond counts, and triggering garbage collection during trades or decision making can cause unpredictable pauses affecting the performance. So we should avoid manual triggering garbage collection at such critical paths and manage memory only at the strategic points when no trades are happening. Or let us say we have an example where we are building a real-time system processing, where a real-time system processing sensor data which is coming at a high frequency, let us say from some IoT device, and garbage collection pauses can cause data processing delays leading to the missed events, and it can cause inaccurate results in that. So it's better to avoid manual triggering garbage collection, and if needed, we can plan it during a low activity periods or when the stream is paused. So for most typical use cases, Python's automatic garbage collection does a great job of keeping memory usage in check, but mastering these techniques can surely help us improve the performance of our application. So with this, we'd like to end our talk. Thank you, everyone.
Thank you. We hope this helps. We are open for any Q&A.
For anyone who has any questions, you can ask today.
I have two questions. The first one, does the reference come affecting async IO too? And the second one is, should we implementing the Dell so we don't have to rely on manually calling the base collection?
I'm sorry, what was your first question again?
The first one is the reference counting IO affecting async IO. And the second question is, should we implement the data Dell? So we should not rely on manually calling the base collection.
Right. So, as mentioned, in cases of asynchronous input-output, or again multi-threading systems, or if you use ASIO libraries or some similar thing which is there in Python, definitely there will be a problem where different threads are trying to use the same or use the same object or work on the same object's reference count, but GIL is there and it's implemented within Python. Having said that, we also touched upon why or where GIL can be a load on Python. So that is why there is also a possibility of using disable GIL flag now. Yeah, hope that answers your question.
For the first question, I still confused. Async IO is reference counting. We use it that multi-threads affecting take the reference icon, right? Because it can.
It's idempotent, yeah. Yeah.
Because it can raise condition.
Right.
What happens if we use async IOs also have the same effect like
So in that case, right. So if I understand your question correctly, Python does provide the automated garbage collector in Python does provide GIL for that very use case. GIL is the global interpreter lock, which ensures that it will lock the thread one, and then, yeah, okay. You want to add something?
Yeah.
Sorry?
Yeah.
Based on my understanding in the slide, by default, for example, if I have X variable X variable and we have some data, then I use Y equal X. We will change the Y will reference count to X, right? How about I don't want to reference count to X, but I want to like copy the value of X, and I can do that.
So you mean something like deep copy or shallow copies?
Oh, yes.
Yeah. So in that case, do you want to take that?
can take.
So in that case, what happens is generally when, let's say, y is namaste and x again points to y, then there'll be no, so both these x and y variables will be pointing to that very same location. But if you want something like a shallow copy, which still does not point to the same reference, then in that case you can have them in container forms, right? In immutable forms like lists or dictionaries, so that it still doesn't point to the same. Or if you have like very long strings, then also object returning does not work.
Just to add upon that, like when you do a copy of that, until and unless you change that value, it will both point to the same memory location. And as soon as you change the copy, like to some other value, the Python will automatically create a new memory slot for that and point to that. So that will be handled like that. Yeah.
Thank you.
Yeah.
So my question is, so how does the garbage collector behave if we are using any other library that is integrated in any other language, like in like POC?
Sorry, come again.
So how does GC behave if we use any library that is written in other languages, like in POC and it has like Python 20? So how does GCP export those libraries like if we assign it variables, internal things? If we can like if we call like GC collect, then I guess GC can intervene that libraries never possible.
No. Python, as far as my understanding, like as per my knowledge, Python won't be able to intervene into some other implementation. It just tracks all the objects which it has access to. Like, so I don't think that it will be able to intervene. But yeah, surely I need to check on that also. Like, yeah. Anything else?
When you're creating a surfaces, right, usually things get complicated and it's pretty hard to figure out where you should do the garbage collection. Do you have any this analysis on whether or not you should do more garbage collection on this service?
Yeah. Yeah, for that we like mentioned your question is when should we actually do the garbage collection?
Basically, when how do you figure out that actually this service is being sold because the garbage collection is not being done properly?
Right. So for that, there are various libraries like trace malloc and other memory profilers, which we haven't covered in our slide, not scope of the presentation, but definitely there are some profilers through which you can find out if it's taking space or if it's taking more time. So those profilers can help us collate those points, whether it's really memory which is taking space and time and hampering the performance. Yeah.
Any other questions, everyone?
Thank you, everyone. This was our first Pycon. Thanks for all your love. Thank you.
All right, thank you so much again to Sajal Gupta and Sajan Gupta for the insightful presentation. And thank you so much for answering the questions as well. And we hope you find the session insightful and have a great day, everyone. See you again on tomorrow's Pycon APAC 2024. Thank you.
Thank you.
Sorry, I couldn't take your photo in this because it's apparently locked. But I actually take out some of your
I saw. Thank you so much for taking some videos. Thank you. Yeah. Absolutely.
Okay.